Welcome back to the course of chemical crystallography, and you can see I am starting with the same slide in which we stopped in the previous lecture. So this is how the characteristic radiations are generated. So now the question is, how do we use one of these characteristic radiations and do our experiment? So for that, nature has also given us the tool. Suppose if we are using copper as a source, if we are using the copper tube, we need to use this copper K alpha radiation and we should eliminate the corresponding K beta radiation. So how can one do that? This copper has the atomic number Z, and if we use the element which has atomic number Z minus 1, that particular element turns out to be nickel. This nickel can be used as a filter which will eliminate the radiation of K beta from copper. So as a result, if we use a nickel filter in front of this X-ray beam, so what comes out will be filtered, and as a result we will get only copper K alpha radiation. So similarly for molybdenum also we can use the filter that is having Z equal to 1 minus Z minus 1, that is niobium, as a filter. So in the laboratory sources, we have a variety of X-ray sources. We can use sealed tube X-ray sources, and in that also we have two options: a fine focus and a micro focus source. A fine focus source with copper, molybdenum or silver anode generally operates at around 50 kilovolt and 40 milliamps, and it gives you about 2 kilowatt of energy, and that is the most common source of radiation that we use in many X-ray diffractometer laboratories. The modern X-ray diffractometers come with microfocus sources where the X-ray beam, the beam that comes out of the tube, is focused on the X-ray, on the crystal. As a result of this focusing, the intensity of the beam on the crystal increases. So if we assume the intensity of X-rays of that kind of power on the crystal is giving you about 1 into 10 to the power 7 photons per second per millimeter square, the same flux that we will get on the crystal using microfocus source will increase to about 1 into 10 to the power 8 photons per second per millimeter square. So that means we will get about 10 times increase in the intensity of that beam on the crystal. As a result, what will happen is it will reduce our data collection time. So with the advantage of microfocus sources, we can collect data at much faster time instead of spending several hours using a standard X-ray tube. The next higher intensity source is a rotating anode based source, where the anode that we have talked about in the previous class, which was actually fixed, here the anode rotates at very high speed at about 10,000 rpm, and then we can use a much higher flux of electrons falling on the anode, which then generates X-rays in the range falling at about 1 into 10 to the power 10, sometimes even 10 to the power 11 photons per second per square millimeter. So now these microfocused based rotating and microfocused rotating anode based sources can lead to enormous high energy on the crystal and reducing the data collection time to about 20 to 30 minutes. Whereas in case of a seal tube source, the data collection time was about 6 to 8 hours. With microfocus source, it can come down to 2 to 3 hours. And now with rotating anode, this can be done in 20 to 30 minutes. The further advancement of this source has come up with a metal jet source where liquid gallium is used as a source, and with this we could achieve the intensity very similar to this 10 to the power 11 to 10 to the power 12 photons per second per square millimeter, and it gives you a very high intensity on the source on the crystal. As a result, the data collection time further reduces. As a result, we can collect large number of crystal data in one day, and as I indicated in the previous lecture, for determination of electron densities in between the two molecules in crystalline state, we need to collect data up to a very high angle of 2 theta. So in that case, we need to collect a large amount of data, and that kind of data using a standard fine focus source may take about 4 to 5 days. A microfocus source can do it in about 2 to 3 days. A rotating anode can do it in about a day, and this may be able to do it less than 1 day. So that kind of advancement can be achieved with a very high intensity source. The next higher intensity source that we can think of is synchrotron radiation, which is not available in most of the countries. There are very few number of synchrotron facilities around the world, but as you may be aware that synchrotron radiation is the electromagnetic radiation emitted when charged particles are subjected to an acceleration perpendicular to their velocity. And this is produced using bending magnets, undulators and wigglers when the electrons are made to travel in a circular path under vacuum at very high velocity. So the emission that we get while bending these electrons from their path is called the synchrotron radiation, which may be achieved artificially in synchrotron or storage rings or naturally by fast electrons moving through magnetic fields. The radiation produced in this way has characteristic polarization, and the wavelength generated can span over the entire range of electromagnetic spectrum depending on the strength of the magnets or undulators or wigglers that are used to bend the highly accelerated electrons. So one can do experiments in UV region, one can do in visible region, one can do experiments in IR and so on, and for X-rays we use these wave intensity, these synchrotron facilities in the range of about 0.2 to 0.3 angstrom to 1.8 to 2 angstrom wavelength region. So now let us know a little bit about the beginning of X-ray diffraction, which is now about 104-5 years old. In 1914, Max von Laue first received his Nobel Prize in Physics for the discovery of the phenomena that X-rays are being diffracted by a crystalline material. He was the first person to show that the X-rays can be used to characterize crystalline materials. Following his discovery and explanation, two people, William Lawrence Bragg, a British physicist, and his father, William Henry Bragg, they introduced Bragg's law of X-ray diffraction, and both were simultaneously awarded Nobel Prize in Physics in 1915 for their services in the analysis of crystal structure by means of X-ray, an important step in the development of X-ray crystallography. So you can see the photographs of Professor Laue and William Bragg and Henry Lawrence Bragg. William Lawrence Bragg and William Henry Bragg. And here is the very simple formula that they proposed by seeing that X-ray diffraction pattern from crystalline materials are characteristic of the compound that are being analyzed. So, in this particular simple expression, which we will derive in a later class, it shows that it has relationship with theta, that is the angle of diffraction. This DH scale indicates the interplanar spacing in the material that we are talking about, and the lambda, that is the wavelength of experiment. So, if we use copper, the lambda value is 1.54, if we use molybdenum it is 0.71 and so on, and this n is an integer. In general we take it as 1 because we only talk about first order reflection, but this n can be second order, third order or nth order reflection. So, that is the order of reflection n. So, now how do we know what sample is crystalline or a sample is amorphous by doing any X-ray diffraction analysis? When we shine X-rays on a crystalline substance, we can record its powder X-ray diffraction pattern, and the pattern would look like the way I am drawing. We plot intensity in the y-axis and the 2 theta, that angle of diffraction, in the x-axis, and for a crystalline substance this would result into a pattern like this with some peaks, some gap and some tall peaks and so on. So, this wavy peaky background signal is coming from a crystalline substance. If this particular compound was amorphous, we would have either seen something like this or maybe something like that, or anything of this sort where you don't see any peak, but what you see is just a hump. So, this particular phenomena distinguishes a crystalline substance from a non-crystalline substance, amorphous substance. Now, the important aspect is that what is the significance of those peaks? You are seeing that the crystalline material has peaks, and wherever there is nothing, there is a very flat background. So, these peaks signify the interplanar spacings that are responsible for X-ray diffraction following Bragg's law. So, in a future class we will discuss about these peaks, how to identify those peaks, how to what gives rise to those peaks during the X-ray diffraction. So, in the next part of today's lecture, we will start understanding the concepts about unit cells, crystal lattice and crystal systems in 1D, 2D and 3D, crystallographic symmetry elements and their differences from the molecular symmetry elements, crystallographic point groups and space groups, and in the following lectures we will continue these crystallographic planes, directions and their significance. So, first of all, what is a crystal? A crystalline material is one in which the atoms or ions are situated in a repeating array over the large atomic distances in 3D. So, suppose in this room we have one atom at this particular position, in the next room on my right it will have the same position, in the following room on the further right we will have the same atom. So, this is periodic in one direction, and the same periodicity is valid in both x, y and z direction. So, that periodicity is the most important aspect in crystal structure, and that has to be always maintained to have a crystal lattice. So, what is a lattice? A lattice is a 3-dimensional array of points in space at constant translational symmetry along x, y and z. What is a crystal? A crystal is a combination of lattice with a motif, which is the association of atoms, groups of atoms or ions. So, a crystal is formed with a particular lattice having a particular three-dimensional separation, and then the three-dimensional array has a set of molecules or ions placed at equal distance in 3 dimension. What is unit cell? Unit cell is the smallest repeat unit in the crystal structure that is repeated in 3 dimension x, y and z, and inside the unit cells have the elements, molecules, ions present in that, and those molecules, ions follow a particular symmetry inside the unit cell, and that symmetry is then maintained in 3 dimension in all the unit cells adjacent to it. So, that is how the crystal lattice is grown. So, when we try to understand that what are the different types of lattices possible, we need to know about the crystal systems. Crystal systems are understood by 6 parameters, namely A, B, C, alpha, beta and gamma. A, B, C are the edge lengths and alpha, beta, gamma are the angles between the edge lengths. So, now to remember this easily, if I write A, B, C in a triangular manner and write alpha opposite to A, beta opposite to B and gamma opposite to C, and then form the circle, then it means the angle between A and B is gamma, angle between B and C is alpha, and the angle between C and A is beta. So, now if I try to draw a very general lattice, which is a total non-symmetric lattice where A, B, C are not same, alpha, beta, gamma are not same, and this particular direction is x, this direction is called the y, and this direction is called the z direction. So, here the distance along x is called A, the distance along y is called B, and the distance along z is called C. So, the angle between A and B is gamma, angle between B and C is alpha, and the angle between C and A is called the beta. Is it clear? So, in this case, we need to remember this strategy, how we identify these A, B and C along with the corresponding directions. So, now based on these 6 parameters which we talked about, the lattice parameters A, B, C and the angles alpha, beta and gamma, we can identify crystal systems in 7 different groups. The most symmetric one that we are familiar with is a cubic system, where the edge lengths are A, B and C all are same, A equal to B equal to C, and the angles alpha, beta, gamma are all equal and 90 degree. So, this is called the cubic system. The next symmetric is the trigonal, where A equal to B equal to C, alpha equal to beta equal to gamma, but not equal to 90 degree. How do we get a trigonal system? If we take a cube and then distort it along the diagonal, the edge lengths will not change, but the three angles will change simultaneously in the same manner, resulting into a trigonal system. This trigonal system can be arranged in two different ways. We can consider as alpha beta equal to 90 degree and gamma 120 degree, but it is one type of lattice. The next symmetric is hexagonal, where A equal to B not equal to C, alpha and beta are 90 degree and gamma is 120 degree. The next one is tetragonal, where A equal to B not equal to C, but alpha, beta, gamma are all 90 degree. The next one in symmetry line comes as orthorhombic. Now you see that the similarity of ABC is broken. A not equal to B not equal to C, alpha, beta and gamma all are equal and 90 degree. The second from the bottom is monoclinic, where A, B, C are not same, alpha and gamma are 90 degree and beta is not 90 degree. And the most unsymmetrical is triclinic, where this A, B, C's are not same, alpha, beta, gamma are also not 90 degree. So this most unsymmetric to most symmetric crystal systems are identified here. Now these crystal systems, which we are talking about, the lattices, can have centerings. So when we have a cube which has 8 corners, so in case of that, if you have atoms or molecules associated with the corners only, that lattice is called the primitive lattice. So this primitive lattice is the most common lattice that is observed, and as you see here in the second column where we identified lattice centering, every system has a primitive type of lattice, which is here primitive, monoclinic has a primitive, orthorhombic has tetragonal, hexagonal, trigonal and primitive in case of cube. Now then, if we have the center of the cube also having one particular atom or group of atoms as same as that of the cube cornered atoms, we call it as the body centered lattice or I lattice. So that body centered lattice is present in monoclinic, orthorhombic, tetragonal and cubic. The next type of lattice that one can think of is a face centered lattice, which actually means that along with the 8 corner atoms, what we have are atoms at faces of every side. So those 6 faces have 6 atoms located at the center of the face. So this becomes a face centered lattice. We write it as F. So in this case, what we see is in case of orthorhombic we have a face centered lattice, and in case of cubic we have a face centered lattice. So now what we have here in case of monoclinic system is that the monoclinic C and monoclinic I lattice are one and the same, and in case of orthorhombic I have A lattice. This C lattice indicates that in case of monoclinic system only, we consider the B axis to be unique. That is why the beta angle is non 90 degree, and when we say beta is non-90, B is the unique axis, then the plane which is perpendicular to C, that is the plane AB, which the face is perpendicular to C, is centered, and that C-centered lattice is considered as one of the Bravais lattices. I have seen C or I, so we will see how a C-centered lattice can be converted to I-centered lattice in the next lecture. And here in case of orthorhombic we have A-centered lattice. See, in case of orthorhombic you have three sides A, B and C, and they are not same. So conventionally, if only one parallel face of orthorhombic lattice is centered, that lattice is termed as A lattice, and that particular face is designated to be the A face. That means it is the BC plane in which this atom is centered. So now if we try to count how many different lattices are possible in case of these 7 crystal systems. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 and 14. So these are called the 14 Bravais lattices that are possible out of these 7 crystal systems. Now on the extreme right hand side column I have highlighted the lattice symmetry or the Laue symmetry of these groups, and we see that the symmetries that are indicated here are 1 bar, 2 by M, MMM, 4 by MMM, 6 by MMM, 3 bar M and M3M. So we will discuss about these when we get to know about the crystallographic point groups and how these notations are introduced in this particular type of understanding. So when one knows how the lattice parameters can be varied for different systems, we need to know about how to calculate the volume of those lattices. Here are some standard formula that we use to determine the volume of these crystal lattices. For cubic, the system is very simple, it is A cube. For tetragonal, it becomes A square C, orthorhombic is ABC, and then when you come to hexagonal, as the angle becomes non-90 degree, we get to more complicated formula like 0.866 A square C. I would like you to look at a textbook how to derive this, because we do not have enough time to derive all these in the particular course. And then as and when the symmetry reduces from trigonal to monoclinic to triclinic, you can see the formula becomes really complicated to determine the unit cell volume, but these are all required to determine the volume of these crystal structures. So in this part of the lecture we have discussed about the generation of X-rays, we have talked about how the lattices are there, Bravais lattices, and the volumes of unit cells. In the following lecture we will talk about crystallographic symmetry.